All right. So to start out, everything should be graded on Canvas now, with the exception of if you want to, submit any of those online quizzes that you had zeros in or that you kind of missed. You can do that by the end of the day today. Once today is over, I'll kind of get those scores reflected on Canvas that kind of even though you submitted them late, that they'll count. I've got the cells graded. I also have exam 2's graded, or the short exam 2, the short answer part on exam 1 graded. So the average was right around a 75. I think it was like 75 point something. The average grade in the class is like a 78.5. So the grade that you're seeing will be, I included the weights on all the categories, and I've treated the exam as though it's going to be your best exam, right? So it counts for 30%. Now, obviously, if you didn't do well on that exam, it's going to kind of give you a grade that's quite a bit lower than what it could be if you do better on the next 2 exams. Because if you do better on the next 2 exams, it lowers the weight of that exam that'll be your worst, all the way down to 10%. So it's kind of worst case scenario for you if you didn't do well on the exam. Also, if you have any missing assignments, it's kind of reflecting that, and I haven't dropped the lowest of each type. I can't do that until we have all of them turned in. And so it's kind of worst case scenario if you have any missing assignments as well, okay? If you have any questions over the grading, feel free to contact me. But yeah, it will kind of overstate, kind of give you worst case scenario if you have a missing assignment or you didn't do well in that first exam, okay? All right, if there's no questions. I'm recording it, okay, good. So we'll get the chat, so when I pull it up, it'll be over here, and we'll jump into things. So last class, we left off talking about the normal distribution. I think I might have briefly mentioned this guy who's really kind of pivotal in kind of discovery and better understanding of the normal distribution, which is why we sometimes call it the Gaussian distribution. Right? So really smart guy. Kind of one of the stories about him is when he was a kid, misbehaving in class, teacher tells him, go over in the corner, add numbers up from 1 to 100, thinking it's going to take him forever. Comes back in a matter of seconds and he's got the right answer. Right? So how could he do this so quickly, right? 1 plus 2 is 3, plus 3 is 6, plus 4 is 10. How did he do that so quickly? Well, what he realized was 1 plus 100 is 101. 2 plus 99 is 101. 3 plus 98 is all the way down to 50 plus 51 is 101. So you have 50 pairs of 101. 50 times 101 is 5,050, right? So really smart guy, like even as a kid was able to kind of think about mathematics this way. There's actually a formal equation. If you want to add up from 1 to any number, this formula will actually tell you what they add up to. But just a really, really smart guy, right? So it kind of leads us into talking about the Gaussian or the normal distribution, or what we sometimes call the bell curve, right? So last class, I think we left off, I mentioned there's a lot of things that pop up in nature: human height, rainfall, temperatures, weight, human performance in general, right? And they document all this in this book and find that probability density function for the normal distribution, which we said we're not going to necessarily be using this specifically, but it'll always kind of be floating around in the background. So I think where we did leave off is saying, okay, look, there's 2 things that can change what this density function looks like. Those 2 things would be the variance and the mean. So even though we might have a normally distributed variable, we could have, the same, we could look at human height. Male and female height are both normally distributed, but they have different means and variances, right? So the normal distribution is defined by the mean and the variance. Now, if we think about the mean, I think we might have went through this, but a quick review as well. Also something to keep in mind today is, remember, this normal distribution, the mean is equal to the median is equal to the mode, which makes it symmetric. So if I had the mean here, this distribution folds on top of itself, essentially. And we'll use that a little bit as we get to some later examples in class. So it's defined by the mean and the variance. So how does the mean change the normal distribution we're looking at? Well, really, if I think about maybe here I've got male height, and here's the average male height. Female height might have the same, if it had the same variance, but just a lower mean, all a different mean does is shift that normal distribution along the x-axis, right? So the mean being different just changes where this distribution is centered at, right? It just kind of shifts it to the right or to the left. right? When we think about if it had a higher mean, it would be, shift it to the right. The variance is a little bit different, right? So if I think about, let's say I start out and I have a normally distributed variable and it's got a variance of 5. Okay? If I go to a higher variance, so same mean, notice both these distributions centered on the same mean, but the one with a higher variance, what does that mean? Higher variance means it's more likely we see values further from the mean, less likely we see values around the mean. So notice here, when we have a higher variance, these values that are further from the mean out here, they have a higher probability of occurring than from that distribution where the variance was lower. Right? Think about what's on our y-axis here. We can think about it as kind of reflecting the probabilities of seeing these things. Okay? So also when we have a lower variance, another way of thinking about it is if I go from this blue to this black distribution, when I have a lower variance, that means values around the mean are going to be more likely. So notice for this black distribution with a lower variance, all these values that are really close to the mean, much more likely they occur than for that variance that's higher. Okay? And you can almost think about it if I had an even higher variance, that's just going to make the values around the mean even less likely and the values further from the mean even more likely, right? So basically having a higher variance, what that does is it smushes or it flattens our normal distribution curve. So the mean kind of shifts it to the left or the right, and then the variance kind of smashes it down or pulls it up, makes it more peaked, right? Any questions on that before we keep moving? Okay. So if I looked at a picture like this, I've got male and female height. Which one of these has a higher mean? Well, intuitively we know probably male, but even if I didn't give you these values, you can kind of see the center of this distribution is greater than the center of this distribution, right? So it looks like average female height is about 65, male is about 70, 71. Which one of these, I guess, which gender has kind of a higher variance in their height? Men, right? Because a higher variance means that we get kind of this flatter distribution, making values further from the mean more likely, values around the mean less likely. Here, the male distribution is a little bit shorter, or kind of flattened out a little bit more. Right? You don't think about it necessarily as just the range, right? Because technically, if we're looking at height, male height has a wider range because I think the tallest man is actually taller than the tallest woman, right? But let's assume that we had a room of 100 people and we don't have these super extreme values. Like we don't, like the tallest woman is as tall as the tallest man, shortest woman is as short as the shortest man. That, even if that was true, they'd have the same range, but male height, we would see that the probabilities of being further away from the male mean are higher than females being further away from the female mean. Does that make sense? Kind of? Yeah. So we can kind of see because it's flatter, we have a higher variation in male height than female height here, okay? And we can get all that without having the actual values, right? Just knowing what those two things would do to our distributions. So we said last class, the area under this curve, this normally distributed curve, this normally distributed variable, which gives us this curve. The area under the curve is 1, representing kind of 100%, right? Because it's every possible outcome for x. If we were to add up all those probabilities, it all add up to 1. Now, I'm going to say some things here and just take what I'm saying as being true for now, and I'll prove it to you hopefully by the end of class, or at least I will prove it to you, whether or not you're convinced, I guess. Hopefully I do a good job of that, right? So if I were to go 1 standard deviation above and below the mean, so 1 standard deviation below, 1 standard deviation above, the probability I would be within 1 standard deviation above and 1 standard deviation below, this probability will always be 0.683 or 68%. Okay? So it doesn't matter, as long as I have a normally distributed variable, no matter what the mean is and what the standard deviation is, if I go one standard deviation above and below the mean, the probability that if I choose, say, a person at random, that they have height in between one standard deviation above and below the mean, that probability will always be 0.683. If I go two standard deviations above and below the mean, the probability I'm somewhere in that range is always going to be 0.9544. Now, so what we're really saying here is the probability that I see this random variable take on a value between two standard deviations above and two standard deviations below the mean is about 95%, right? The likelihood is about 95%. Okay. Now, it kind of makes sense that this is larger because if I go two standard deviations above and below the mean, that's just giving me more possible values I could see for X compared to only going one standard deviation above and below, right? So then if I were to go three standard deviations above and below the mean, there's an even higher likelihood that I see the value be somewhere in that range, right? I'm just widening my range here. And so once we get up to three standard deviations above and below the mean, I have like the probability I see something in that range is 0.997, right? Which is what this is really saying is, what's the probability I see something that's even more than three standard deviations below or even more than three standard deviations above? One minus this, so 0.003. So very, very unlikely that we see values for X that are further than three standard deviations away from the mean. Right? So how am I getting these numbers? Right? We'll start to talk about the process. I doubt I'll be able to kind of show you exactly how I got this number today, but I will be on Monday. So if we think about the normal distribution, right, and we know that there's some random variable X, it's normally distributed, and it has this mean and this variance. This is just typically how we write this out in the notation for whatever random variable X we're looking at. It's normally distributed. Here's its mean. Here's its variance. Okay. What we eventually want to get to is dealing with a standard normal distribution. So a standard normal distribution is a special case where the random variable is normally distributed with a mean of 0 and a variance of 1. Okay? Once we have a standard normal distribution, I think I mentioned last class those z tables, we can start to use those standard normal or those z tables. Right? So I like this standard normal distribution because I can then use those tables where someone's already done some of the work for me. But ultimately what I'm going to do is I start out with some random variable X. I know its mean, I know its variance. What I'm then going to do, well, I'll explain it this way first before I talk about z-scores. So if I have this standard normally distributed variable, I could think about that whatever X value I'm looking at, that's how many standard deviations away from the mean I am. Right? So I can think about here, if my mean of this standard normal distribution is 0, and the variance is 1. Well, if the variance is 1, what's the standard deviation? Square root of the variance, square root of 1 is 1. So if I think about looking at some X value, let's say I look at the X value of 1, how many standard deviations away from 0 is the value of 1? Well, it's 1 away from that mean. The standard deviation is 1, so it's 1 standard deviation away. What if I look at the value of -2? Well, if the standard deviation is 1, I'm 2 away from the mean. That's going to be 2 away from the mean, right? 2 below the mean, right? Standard deviation is 1. -2 is 2 standard deviations below the mean. So if we have this standard normally distributed variable, what we're going to start calling this instead of X is Z. And the reason why is because we're going to be converting our typical normal distributions that don't have means of 0 and standard deviations or variances of 1. We're going to be converting them into what we call z-scores, which we know are normally distributed with a mean 0 and a variance of 1. So that's why I have kind of z's down here. Okay, so we'll revisit this, but I kind of introduced this idea of if my variance was 1, so my standard deviation would also be 1. And then I can just start thinking about these values as representing how many standard deviations away from the mean I am. Okay? 1 is 1 standard deviation away from the mean. -2 would be 2 standard deviations below the mean. Negative 1.2 would be 1.2 standard deviations below the mean. Okay? So how do we get these z-scores? So what we're going to do is we're going to take whatever value we're interested in x, we're going to subtract the mean of that normally distributed variable and divide by the standard deviation. Okay? Now I'm thinking about this value for x. This might be something like, what's the probability that if I chose someone at random, they're taller than 70 inches, right? So 70 is my x there. I would then subtract the mean height from 70, divide by the standard deviation in height, then that would give me my z-score, okay? And we'll work through some examples here, but this is the formula that we'll use. The one thing that is nice about once I convert these to z-scores, I know these z-scores will have a mean 0 and a variance of 1, but also the z-score kind of what it reflects, or I guess the definition or what it's telling me, is it's the number of standard deviations away from the mean that value for x is. So if I said, what's the probability, or if I said, look at 70 inches for height, how many standard deviations away from the mean is that? Well, once I convert that value of 70 into a z-score, the z-score will tell me 70 inches is, I don't know, 0.5 standard deviations below the mean, right? So if I see kind of positive values, that's going to tell me that whatever value for x I was looking at was above the mean. If I see negative values, it's going to tell me whatever value for x I was looking at is below the mean. Whatever the actual number of the z value is, say it's 2.3, that's telling me whatever value for x that I converted into a z-score, it's 2.3 standard deviations above the mean, right? And then another kind of nice property, the z-score for the mean is always 0. Think about why. If the value for the cutoff I used was the mean, I'd have the mean minus the mean divided by the standard deviation. Well, the mean minus the mean is 0. So the mean would always have a z-score of 0. If I were to take every single possible value I had for x, convert them all into z-scores, and then plot their distribution, those z-scores will always be a standard normal distribution with a mean of 0 and a variance of 1, okay? So I think what I'm going to try to do here is prove this too. So let's say I have this variable x, and I'm just going to use a small number of values to prove to you why subtracting the mean and dividing by the standard deviation will give us this standard normal distribution. So if I were to find the mean of x here, what would I do? Add these numbers up, divide by the number of numbers I have. So 2 plus 4 plus 6 plus 8 is 20. I've got 4 numbers. I've got a mean of 5. If I wanted to find the variance, I'll kind of write the intermediate steps down just as a reminder, but then I'll kind of erase them. So what would I do? I would take the first value minus the mean, square it, do that for each observation, add them all up, and then divide by, we'll treat this as a population, so divide by the number of numbers we had. So 2 minus 5 is negative 3, squared is 9, 4 minus 5, squared is 1, 6 minus 5, squared is 1, 8 minus 5 is 3, squared is 9. So I add these up, I get 20, and then divide by the number of numbers I have. I happen to choose a value where I have a mean that's the same as the variance, right? Which is okay. So if that's my variance, what's my standard deviation for x? Just the square root of the variance. Right? Variance is 5, standard deviation is square root of 5. So now what I'm going to do, I'm going to turn all these x values into z-scores. Okay? So to find a z-score, I subtract the mean and divide by the standard deviation. So I take the value of 2, I subtract the mean, which is 5, so negative 3, divide by the standard deviation. I've converted that value of 2 into a z-score. Next value, 4 minus the mean, so negative 1, divided by the standard deviation. If I do the next 2, just doing the math in my head here, right? I'll now have every single value for x converted into a z-score. Also, this is a bad 3, sorry. Okay? So now let's say I want to find, not the mean for x, the mean for z. what's the mean of z here? Well, notice, if I add these together, these cancel out, so these actually add up to 0. So 0 divided by 4 is 0. Because I subtracted the mean from each one of my x values to get this z variable, the mean of that new variable will be 0, right? Which is what I said is true about the z-scores, right? We want a standard normal distribution that has a mean 0 and a variance of 1. What about if I find the variance or the standard deviation for this? So the variance of z, well, if I take this, subtract the mean, and then square it, do that for every observation, add them all up, and divide by the number of numbers I have. So -3 over the square root of 5 minus 0, well, that's just -3 over the square root of 5. I'll square that. That would give me 9/5. -1 over the square root of 5 minus 0, well, that's just that value, so plus 1/5. And I do the next, just square the next one, subtract 0 and square them. I'll have these values. If I look at the numerators, they add up to 20. Divided by 5, that's a value of 4. Well, I still have one thing left to do, which is divide by the number of numbers I have. So I end up with a variance of 1. And you can do this in Excel as well. Actually, if we have a little bit of time at the end of class, maybe I'll do that and show you. It doesn't matter what values you have, as long as they're symmetric, so it fits this kind of idea of a normal distribution. When I subtract the mean and I divide by the standard deviation to create these z-scores, the z-scores will always have a mean of 0 and a variance of 1. Excuse me. And you'll never have to go through and do this for all the values, but I'm just trying to kind of give you some support as why that's true. Okay. So we can also think about, if I were to take this variable x and map it out into z-scores, the mean will always have a z-score of 0. If I go one standard deviation above the mean, well, we said the interpretation of the z-score was the number of standard deviations away from the mean. So if I was just to take the value of the mean plus the standard deviation, it should always give me a z-score of 1, because I'm one standard deviation above the mean. If I were to look at 3 standard deviations below the mean, that should give me a z-score of -3. Okay. So why can I map this out? Why does this work? So try to give you a slightly better way of kind of thinking or looking at this. So if I have I'll write this out. So here's my formula, right? The z-score is equal to whatever cutoff value I'm looking at minus the mean divided by the standard deviation. So let's say my x value is 2.2 standard deviations below the mean, right? So I take the mean, I subtract 2.2 times the standard deviation. What will the z-score be? Well, if I plug this in for x, notice, so this is my z-score. I just plugged in what x value I'm interested in. The mean minus the mean, these cancel. I'm left with -2.2, which should be, because this was 2.2 standard deviations below the mean, right? So that's why kind of that z-score interpretation works. Now, in practice, we don't see this. In practice, we would see something like 70, right? We then convert 70 into a z-score, and then it tells us how many standard deviations 70 was away from the mean, right? But if we were able to know how many standard deviations away, that's why once we plug it in, the z-score interpretation works like that. Okay. Any questions up to this point? Make sure there's nothing here in the chat. Okay.
So they work, but is it just so we have a comprehensible value for the standard deviation? So
why do we want the z-scores essentially? Yeah. Okay, so why are we calculating these z-scores? I'll get to it, but we're getting close.
Okay.
Okay, we're getting close. But I just have to kind of go through some of this stuff before we get to the kind of tying it together. Okay, so that's actually, right, what use are these, right? Well, usually all I see is this variable x, and I say, what's the probability that x is between certain values, right? What's the probability that I see somebody, I select someone at random, what's the probability their height is in between 65 and 70 inches, right? Well, the problem is we want to be able to use these standard normal tables, but we can only do that if the variable has a mean of 0 and a variance of 1. So we know that if we convert these x values into z-scores, we can then look them up in the table. So I'll kind of use this value to give you a good visual, right? So let's say we want to find, we're going to do this z value of negative 1.29. So stop this. Maybe this is a better way to think about it, okay? Here's this variable x. I know it's normally distributed. Just to give you some values to make it kind of nice, let's say the average is 71, and I want to know what's the probability I see 68 or something less than that. Okay? Well, I can't use that standard normal table yet, right? And we'll talk about how we use it here in a second, but I can't use it because it only applies to when I have a mean 0 variance of 1. What I can do is convert these values into z-scores. So once I convert 68 into a z-score, let's say it's negative 1.29, I can then look that z-score up in my standard normal table, and it will give me the probability of seeing that or anything less than that.
Oh, so it's a quicker way to like give you.
Instead of, yeah, because otherwise what I'm doing is I'm integrating that crazy probability density function from negative infinity to 68 to find the area under the curve. I don't want to do that, right? It's a lot easier because the values for the standard normal distribution will always be the same because the mean is always 0, variance is always 1. Yep. Yeah, it's kind of a broader picture, yeah. Okay, so let's say we have that negative 1.29 now. How do I start to use that standard normal or that z table to find probabilities? Okay, so what I'm going to do is, and I'm telling you right now this is the area, but let's look at it, okay? And this is why I said having it in front of you might be easier. This is kind of small. For some of the other examples we have, I'll pull up a different file so I can zoom in, but I have some stuff on this slide I think helps you understand how to use the table. So let's say I want the probability that I see negative 1.29 as my z-score or anything below it, right? The first thing I do is use my row headings to look up the very first decimal point. So negative 1.2. I then use my column headings to look up the second decimal. So 0.09, right? So negative 1.29, the probability that I see that z-score of negative 1.29 or anything below it, right? So this table is telling us the cumulative density. So whatever z value I look up, it's the probability of seeing that z value or anything below it. Or you can think about it as the area to the left of that z value. Right? Less than or equal to. Yep. So the probability of seeing the z value be negative 1.29 or lower, or you can think of less than or equal to negative 1.29, 0.0985. Okay. So when I looked that value up, this blue area here was 0.0985. Okay. So what if we wanted to find the probability we were less than or equal to positive 1.29? So there's two sides to that table. The first one is negative values. The second one will be positive values, okay? If I look up 1.29, it's the same process. 1.2, go over to 0.09, so 1.29. The probability I see that or anything below it is 0.9015, okay? Are we okay with kind of how we use those row and columns to look it up? So, one thing we can think about here is, because I have these two values, I'll hold off on that discussion. We'll make sure we understand how to use this first. So we can find these probabilities of whatever z value we look up or anything lower, right? Less than or equal to those values, okay? So You can kind of think about that visually, right? If you're drawing this out, plot the 1.29, you want the area to the left. Okay? Now, one thing I want to mention here real quick is, I'm going to skip this slide for a second. Here we go. So if I remember that this is a symmetric distribution, when I look at that z-score of 0, that's my mean. It exactly splits my distribution in half. The probability that I see something to the left or the right of the mean should both be 0.5, right? If this is splits my distribution in half and my standard normal distribution, that mean is 0. So the area to the left of 0 and the area to the right of 0 should be 0.5. So when I'm drawing things out, and I draw it out and it looks like this, and I plot my z-value, automatically I know that the probability of seeing 1.29 or anything below that has to be greater than 0.5, right? Because if I just think about the area to the left of 0, that area is 0.5, I want something larger than that, right? So anytime I have a positive z-value, actually, good visual here, so I'm looking at z-scores. I know the area to the left of 0, or left of the mean, is 0.5. So it doesn't matter which one of these positive z-scores I look at. If I think about the area to the left of them, they're all going to be areas that were larger than just the area to the left of 0. So for every positive z-value, when I look it up in the table, I should find something that's greater than 0.5. If I looked up negative z-values, and I want the area to the left, those values will always be less than 0.5. Mm-hmm. So, improve this. Oh, did not want to do that. I can prove this by going to the tables. Notice for the positive z-values, every value is greater than 0.5. Then when I look at the negative z-values, all the areas to the left are less than 0.5. And if I go to 0, so 0.00, exactly 0.5, okay? So that's one thing that's kind of nice, just to make sure we don't make some easy mistakes as we get into some of these problems today and also on Monday. So I also put these up here. We'll start seeing, I used like 1.29 already. We'll start seeing these z-values a lot. They just end up being common because the area to the left of them is about 90, approximately 95, 97.5, 99, 99.5%, right? So we'll be seeing these same z-values pop up a lot. So if you're like, why do I keep? Well, it's because we're usually interested in these cutoffs, right? Okay, so what if we go up here, let's say instead of the probability that x, or that the z-score is less than 1.29, if instead of wanting the probability that it's less than or equal to that, what if I wanted the probability that it's greater than 1.29? How could I find that if I look up positive 1.29 and find 0.9015? Yeah, just 1 minus 0.9015, because the area under the curve is 1. So we would just take this blue area, subtract it from 1, and what we're left with is this white area on the right-hand side. Okay? So we can only ever use that table to find the area to the left, but if we can find the area to the left of something, it's very easy to get the area to the right. We just subtract the area to the left from 1, okay? And that's kind of what I have here, right? If I want the probability I'm greater, 1 minus the probability that I'm less than that, right? And we kind of talk about that blue area minus 1, give me 0.095. Now, another thing I want to point out here is, well, do I want to do it here? I'll wait. I keep getting ahead of myself because I really want to show you guys this, but I think I have another example set up. Yeah, I'll do it with this example. So here's our table. What if I want the probability that I see a z-score greater than or equal to negative 2.53? Well, first of all, before I even go to the table, let's just draw this out, okay? And kind of get our bearings about it. So I know that if I'm dealing with z-values, I have a standard normal distribution with a mean of 0. I just said, what's the probability I see negative 2.53 or greater, right? So what do I know that probability has to be greater than? Yeah, 0.5. because the area to the right of that mean of 0 is 0.5, so the area to the right of negative 2.5, well, that's a larger area, it has to be greater than 0.5, right? So if I look at those possible answers, I can rule out B and C. C I could have ruled out because I'm looking for a probability. It has to be non-negative, right? 0 or higher. Well, 0 up to 1, right? So I can rule out B and C. I can actually, and we're probably not comfortable enough with the standard normal distribution yet to rule A out. But if I start to think about, okay, if I were to look up the probability that to the right of a certain z-score, and when I find that probability, it's 0.5057, what would have to be true about the z-score that would give me that area to the right of 0.5057? Well, the area to the right of 0 is 0.5, so it would have to be just, really close to that mean, probably like negative 0.2 or negative 0.1. It would have to be a z value that was very close to 0. Now, I said we're not probably comfortable enough with z-scores yet to know that 2.5 is very far away, right? I mean, we talked about if we just went out 2 standard deviations above and below, that was already like 95% of the values were in that range, which meant only 5% were outside of it. So being 2.5 standard deviations away from the mean, this area, this likelihood is going to be very small, right? Which means, conversely, if this area is really small, what has to be true about this area? It's going to be large, right? 1 minus that, or closer to 1. I shouldn't say really large. It's going to be closer to 1. But I can look up negative 2.53 in my table. So we'll go here. Negative 2.5, and I believe this is the 3 column. Yep, so negative 2.53. So the area to the left is 0.0057, okay? So this area is 0.0057, which means the area to the right is 1 minus that, right? So what, 0.9943? Okay. So that's how we would find the probability of being greater than or equal to a certain value, okay? Now, what if I wanted the probability I was less than or equal to? Well, we actually kind of inadvertently already found that, right? That was one of the components to finding this. So if we look up negative 2.53, that was where we found 0.0057, which would have been exactly what we wanted, okay? Now, I want to show you something else with this, though. We're going to keep using these same values, but I want to remind you of something that's really nice and kind of can save us some work about the standard normal distribution. So when I looked up negative 2.53, the area to the left was 0.0057. What would the area to the right of positive 2.53 be? Well, remember, this is a symmetric distribution. So if I were to fold this in half around the mean, this would lay exactly on top of each other. So this should actually be also 0.0057. Now I can prove this to myself because if I look up the area to the left of 2.53 and then subtract it from 1, it should give me this area here. And if that's not 0.0057 when I do this, I've got a problem, right? So I go ahead, all right, I'm going to prove this to myself. I go to the table. I look up positive 2.53, maybe. So here's my 0.3 column. So I go down here, 2.53. The area to the left is 0.9943, okay? So 0.9943. So if I want to find the area to the right, I have to subtract that from 1. Sure enough, if I do that, I get 0.0057. Okay? So knowing this is a symmetric distribution can sometimes help us. As we work through more examples, we'll see a lot of the times, maybe I want both sides, right? I want the area less than negative 2.53, and I want the area that's greater than positive 2.53. Okay? But I didn't even really have to look that up if I remember the symmetric distribution. Okay. Any questions over that? Excuse me. We're okay with that? All right, so a couple things I wanted to talk about. I brought in some stuff I thought was kind of interesting. So I had this huge survey data of like 12,000 people, and I can't remember which gender I looked at. It was men or women, one of the two. I then just put this into a histogram, and I actually only did this by inch, so this isn't even really nice, too continuous. I could have made it more continuous. And kind of notice it follows, if I try to shape this out, pretty close to a nice normal bell curve, right? Another one I thought was interesting, so that CrossFit puts this stuff out. I don't know, some workout they had. I don't know what it was called. It's not in here. Doesn't really matter. So some workout they had, and then kind of how many reps or how well people performed. And what was really interesting is like human performance in this workout. I mean, women, it's almost, I couldn't draw by hand a better normal distribution than this, right? Men's a little wonky, kind of right here and right here, but pretty close to a nice normal distribution. So once again, we start looking at things that occur biologically. A lot of times we see these variables look pretty close to a normal distribution. So the other thing I thought was kind of interesting to kind of tie in just generally how we should be thinking about statistics. I have this powerlifting data set with like, I don't know, tons of different powerlifting meets that have occurred. And I don't know, I kind of got to thinking, I've heard people, maybe I had read something about whether or not men and women had different potentials for strength or something. And I was like, well, I could kind of use this data and play around with it. So they have one lift, which is the deadlift. And if we look at kind of the distributions, maybe a little bit of a right skew, but like pretty close to like a normal distribution, right? In fact, some of these really high values would be balanced out by really low values if we had like people that weren't good at the competitions, right? So pretty close to normally distributed, but notice kind of the average female lift is much lower than the average male lift. And now that I look at these numbers, it might not have been deadlift. It might have been kind of the combination of their three lifts. But regardless, it doesn't matter. So we see that kind of the male amount lifted is higher. But if you take a look at this data set, there's a lot more 300+ pound men in the data set than there are 300+ pound women, right? And so in fact, some of the guys are like over like 400 pounds. So it's like, maybe I should, be factoring in that weight, right? Because if I just talk about total amount lifted, the larger someone is, probably the larger mass they can move. Right? So they have this thing called a Wilks score that they actually do calculate in powerlifting, which essentially the idea is they try to take the amount lifted and basically divide it by how much the person weighed. It's a little bit more complicated than that, but it's essentially trying to give you a per pound strength measure, right? So if you factor in the weight of these lifters on their lift, and you get this Wilks score, once again, nice normal distributions, especially this one. But now the mean is just below 400 for women, and it's actually just below 400 for men. Right? There might be a slight difference there, but looking at the actual means, it's very close. Right? So I thought this is kind of an interesting thing to look at and say, well, look, if I try to use this data to tell the story, I kind of make it look like men are way stronger than women or have capacity to be stronger. But if I actually look at per pound strength, it's the same across both genders, right? I mean, it's very, very close. Now, one thing that's interesting is we look at kind of the height of this. This is, I didn't draw them on the same thing. This is a little flatter, right? 0.006. This one's a little bit 0.007. So this one actually has a higher variance, male performance. So there's actually a little bit more variation in female performance here than there is in male. But they both kind of follow this nice normal distribution. It's kind of a fun little example, some of the things that we've talked about. Okay. All right, are there any questions kind of over any of the stuff we did towards the end? Hopefully, like going through a few of these examples, we're feeling comfortable using the table, because on Monday, we're gonna go through examples where we kind of are looking for different areas under the curve, and we're going to use the table to find even sometimes multiple probabilities in order for us to be able to get what we eventually want. So hopefully we'll at least understand the mechanics of this standard normal distribution. Like I said, from here on out, maybe having it printed out is a little bit easier. And I will, pull it up, but as I scroll, right, in order for it to be big enough, it sometimes takes away the column headings, and so then you're kind of like, oh, which one was that? And I'll try to scroll up and do as best as I can, but it might be easier to have it in front of you. Okay? So get on. If you had any online quizzes that you missed, go back. You can submit them by the end of the night. Complete your Learn Smart assignment, Chapter 6, by the end of the night tonight as well. And then I will post an online quiz that also has to be completed prior to the start of Monday's class. Okay? All right. See you guys on Monday, and I will answer the questions here. Yeah, so we'll have a quiz. I'll post one as soon as I get back to my office.